Today, I want to talk about floating point numbers. I want to start from 0 and hopefully we can work our way up to have a good enough understanding of the format to be able to re-implement some basic operations on floating point numbers. The way I want to do this, I want to start by just looking at the bit representation. So just take a couple of floating point values and simply print their bit representation. Then I want to go a bit further and kind of try to understand the relationship between the floating point representation of a certain number and its just integer bit representation, taking the same bits and interpreting them as an integer. And just see what we can learn from that. Then I think we should have a good enough understanding to be able to implement a simple floating point operation. And that's going to be the floating point add operation. And I hope that by that point, we have enough knowledge to start to do something a bit harder than that. I want to try to kind of rederive, to kind of build up from our understanding to be able to implement the inverse square root algorithm that was used in Quake 3. And I think that's basically all I want to do. So let's get started. Let's just create a C file. And in here, I want to include standard IO. And let's first just make sure that this even compiles. Looks good. And now I want to look at a couple of floating point values and their corresponding bit representation. So how are we going to do that? Printing a floating point value is very easy. But how do we get the bit representation of this floating point value? Now, if you are familiar with C, you might have seen a certain technique for this before, which is to create a variable of that type, print the float, and to get this floating point value as a different type, but using the same bits, you would take the address, you would convert this now floating point pointer to an unsigned integer pointer, and then dereference that unsigned integer pointer. Now for this, I have to first include standard int. And let's see if this works. All right, we get our bit representation. Let's actually print this as a hex value. All right. Now, the problem with this technique is that it's actually undefined behavior. In C, you aren't allowed to take a pointer to a certain type and just cast that pointer to be a pointer of a different type. It is allowed for, there are a couple of exceptions. For example, you are allowed to take every pointer and cast it to a character pointer. And you are allowed to cast pointers to structs if those structs have common elements, like they start with the same elements. But neither of those are the case here. We're taking a floating point pointer and an integer pointer, and those types are not compatible in this way. So we have two ways of solving that. The first one goes like this. You create a variable of the type that you want to cast to. And then you simply mem copy into that variable from your original value. And you use the size of either in this case, but I'm just going to take our integer variable. And now you've basically taken the bits of the floating point value and copied them one by one into the integer value. And this is basically what we want. We just want to look at the same bits, but interpret those bits in a different way. And this should give us the same result, except I've forgotten to include string.h. And we get the same value. And this technique works in C and C++. But if you are in C, you actually have one more option, which is to create a union type of the two types that you want to look at. So I'm just going to make our float the first member and our integer the second member. And now I can simply create a variable of this type and assign the floating point value that we want to have a look at to the floating point member. Just print that here. And now we can read the unsigned integer member and basically get the same thing as before. We have one region of memory. So these two members of the union occupy the same 4 bytes in memory. And here we are interpreting them as floating point value. And in this case, we are interpreting them as an unsigned integer. So let's just print that. And again, we get the same value. All right, so let's actually have a look at this value. For the floating point value 1, we get an unsigned integer value where a couple of bits in the higher order bits are set. And let's just try this for another value. Let's, for example, look at the floating point value 2. And here we can kind of see the first interesting thing, which is by adding 1 to our floating point value, we've changed a bit or multiple bits. Again, in the on the most significant bit side of those 32 bits. If we imagine we did the same thing for an unsigned integer, we would have just kind of flipped the least significant bit if all of the bits after that were 0. So this is interesting, and we should keep that in mind. And let's try the same thing for a very high floating point value. Now we have to be careful that we aren't outside of the range, but in this case, I'm going to pick a value that is safely inside the range, the representable range of values. And I'm just going to cast this to a float. Now, 1 shifted to the left by 20 is 1 shifted to the left by 10 times 1 shifted to the left by 10. And 1 shifted to the left by 10 is about 1,000, so 20 is about 1,000,000. Let's have a look at that. All right. And let's try to do the same thing here, where we just increment this value by 1. And this is interesting again. When we were in the lower range of the floating point value, we changed one of the more significant bits. And if we are in the higher range of the floating point value. We've only changed the fourth bit, like the fourth least significant bit. So that's kind of interesting. But let's go a step further and let's try to look at a greater range, or at least to have more values in between to kind of see the progression. And for that, I want to create like a graphical plot of values. And the easiest way to do that is to use matplotlib, or one of the easier ways. But we can't easily cast values as we are trying to do here from a 32-bit float to a 32-bit unsigned integer in Python. So what I'm going to do is I'm going to create a text file where we have two columns, one column of our floating point values, and then another column of the corresponding unsigned integer value. And then in Python, we're just going to read that file line by line, interpret the two columns, create two arrays from that, and then just plot those arrays. So we kind of get the best of both worlds from Python and C. So let's do that. Let's just create a file. I'm just going to call it f.txt, and I'm going to open it in write mode. Don't want to forget to close that. And now we want to iterate through a bunch of floating point values. So I'm just going to create a for loop. Let's start at floating point value 1. And let's go up to, again, about 1 million. Should be good enough for now. And ++ actually works the same way on floating point values. We're incrementing it by 1. But I think I want to make it a bit clearer and actually increment like this. All right. So to print to a file, we're going to use fprintf, give it the file as our first argument. Then we have the format string, which is in our case, same as before, a float, an unsigned integer, next line. And here we're just going to create again our union type variable. Going to assign the iterator float to the floating point member. And we're going to read both members and just print them. And I think that should give us roughly what we want. Let me just check this over. Start at 1, go up to about 1 million. Increment by 1. And we're printing to the file. That looks okay. Actually, I can stay in here. And let's just run this. Actually, can I just... Let's just type this again. Float is not a structure or union. Yes, that is correct. I need to do n. All right. Let's have a look. And this looks pretty good. We have our floating point value in the first column and the corresponding integer representation on the right side. All right. So let's create a Python file to plot those two columns. Just going to do main.py, import matplotlib, pyplot as plt. And as I was mentioning, we're just going to create two arrays for the x and the y values, where x is our floating point dataset, and y is the corresponding integer bit representation. And we're just going to open the file f.txt, this time in read mode. This file, and then we're going to go through this file line by line. Now for each line, we want to split the string of that line along the spaces. So I'm just going to do line.split. And now I want to append to x that string before the space character, interpreted as a float. Like, yeah, we're just going to create a float from that string. So I'm going to do append, create a float from the first element of this string array. And here we're going to take the integer at index 1. And now we should be able to just plot those two arrays and show the plot. Let's try if this works. So this looks very interesting. We can see that we get a plot that looks roughly like a logarithmic function with a couple of important differences. But we can see that this kind of confirms what we saw when we were printing the values, where for higher floating point values, again, on the x-axis, we have our floating point values, and we have an implicit times 10 to the power of 6, so 1 million on the right-hand side. We can see that the difference from one floating point value to that floating point value plus 1, and then converted to the integer bit representation, is going to be much less than in the smaller, like in the range of smaller floats at the beginning of our range. This is kind of the first interesting thing that we can see here. Now, the one important difference to an actual logarithmic function is that a logarithmic function would be equal to 0. The y value would be 0 when the x value is 1, meaning that something to the power of 0 is 1. But here we can see that that is not the fact here. And for now, let's just keep this in the back of our heads. And this is going to be important a bit later. All right. Another interesting thing that we can see here that we can't really explain yet, but we're going to be able to explain that in just a minute, is that we have these flat line segments. I'm just going to zoom in a bit. You can see that there's kind of a flat line segment here and here. And the width of those line segments increases the higher our floating point value is. So that, again, is something interesting to keep in mind. All right. Let's actually have a look at how a 32-bit floating point value is represented in its actual bits. And for that, I want to go back to C. And for now, I'm just going to delete this code. That shouldn't be needed anymore. And let's actually write a comment about that. So the most significant bit in a floating point value is the sign bit. 0 meaning that there's no sign. It's a positive value or 0. Or actually a couple of other options, but we're going to get to that in a second. Then we have 8 bits for the exponent, and then 23 bits for the mantissa. So what does it actually mean? What is the mantissa and what is the exponent? The explanation for that kind of goes hand in hand with how you would actually get the numeric value of this set of bits. So let's just try to do that with an example. Again, our 0 is the sign bit. So if the sign bit is set, we multiply the entire resulting number by -1, otherwise by 1, which is just identity. Multiply that by the rest of the number. And that rest is going to be calculated by taking 2 to the power of our exponent times 1 point, and then our 23 mantissa bits. So we have 1 point and then a series of bits. So let's just kind of try to imagine what happens with different bit configurations. If our mantissa bits are all 0, for now I'm just going to assume that our sign bit is not set, just to so we have to write a little bit less. 2 to the power of our exponent times 1.0. Again, when our mantissa bits are all 0. And that's just 2 to the power of our exponent. If our mantissa bits are all 0, let me just... Then we have a value that is very close, but not quite 2. We have 1 point and then 23 1 bits. And that's going to be slightly less. This is not correct mathematical notation, but I hope it gets the point across. Exponent plus 1. Okay, so when all our mantissa bits are set to 1, we are very close, but not quite at the next exponent value. So the first way we can kind of interpret the floating point representation is that our mantissa acts as kind of an interpolation factor from one exponent value to the one after. Now, how does this work? Actually, let's try to just insert a couple of actual values. So for example, let's say our exponent is the value 2. And our mantissa bits are all 0. Then we just get the value 4, 2 to the power of 2. If again our exponent is 2 and our mantissa bits are all 1, we get a value that is close, but not quite 8. Because we are multiplying 2 to the power of 2 times a value that is almost, but not quite 2. Imagine if our exponent were actually 3. In that case, we would have 2 to the power of 3, so 8. And this is kind of the interpolation that I was referring to. In fact, we can just also do it just to have the reference. The next exponent is 3 multiplied by 1. We just get 8. And if our mantissa bits are some kind of mix of zeros and ones, we get some value between 4 and, again, not 8, not actually 8, but close to 8. The last representable value before 8. All right. How does this work for negative exponents? Let's say we have 2 to the power of -2. And our mantissa is all zeros. Again, our sign bit is not set. 2 to the power of -2 is the same as 1 divided by 2 to the power of 2. And that's just 0.25 or 1 divided by 4. And let's again assume that our mantissa is all ones. 2 to the power of -2 times 1 point, and then 23 ones. We get, this is actually kind of hard to write. Let's do -3 first. 1 divided by 2 to the power of 3. So 0.125. And let's go the other direction as well. 2 to the power of -1. That's just 1 divided by 2 to the power of 1. And this is just 0.5. All right, so if our mantissa bits, let's go back to this example, are all ones, we get, actually let me put it above, because now we actually get close to the value 1 divided by 2. So we're kind of interpolating between 0.25 and 0.5. And then if we are at exponent -1, we're interpolating between 0.5 and 1. So we can see that the smaller our exponent is, so the more we get into the negative exponent range, the smaller the distance is between one exponent value and the next. And the greater it is, the greater also the distance between one exponent value and the next. So for example, for 2 to the power of 2 and 2 to the power of 3, we have a distance of 4, from 4 to 8. And for -3 to -2, we have a distance of 0.125. But we can see, even with negative exponents, we don't get a negative resulting value. We just get values between 0 and 1. Actually, not quite 0. And that's kind of the next question. Let's imagine our exponent is a very small negative value. Small in the sense of very, like in the direction of negative infinity. So 2 to the power of -1000. That's 1 divided by 2 to the power of 1000. And that's really just a very small value, but it's not 0. In fact, we can't get to 0 like this, even if our exponent is very far into the negative range. So how do we get to 0? Well, it turns out that the floating point format has a special value, a special exponent value, where our mantissa is interpreted in a different way. And that special exponent value is when all the bits are set to 0. And we're going to get to how the bit representation of the exponent actually relates to the number in just a second. But for this special exponent value, we have a different rule. And that rule is that our number to the power of this special exponent value is now multiplied by 0 point and then the 23 mantissa bits. And now we can see how we get to 0. because if all our mantissa bits are set to 0, we just get 2 to the power of our special exponent times 0, and that's just 0. So how is our exponent actually represented? Now, if you've worked with numbers before, I guess, you will have heard of the concept of 2's complement. So the way you can represent a negative number, let's just do this for an 8-bit value. You would set the highest bit to 1, and then this value right here would be your most negative value. Meaning, for example, if we have these 8 bits, this would be the value 0, and this would be the value minus 128. Now, if you have this bit set to 1, you would get minus 127. And you just count up like this, as you would with with the positive side of this number. So this is minus 126, and so on. Which means your, the value minus 1 would be represented as all ones. And this allows you to have basically an easier job implementing arithmetic operations with arithmetic operations that work the same on signed and unsigned numbers. But it turns out that the floating point exponent is represented in a different way. It's represented in a biased representation, meaning that to get its actual numeric value, you take the bit value, convert it to an unsigned integer, and then you, in this case, subtract a certain value from that. And that certain value, the bias, in this case, is 127. So if we have some value, for example, the value 1, the way we would get the actual exponent value is by taking the value 1, subtract our bias of 127, and we get minus 126. And I said earlier that if all bits are set to 0, that is actually a special case for this exponent, where we still take the number minus 126 as our exponent. So up here, where I said x, it should be minus 126. But we interpret our mantissa as being the numbers after the binary point and after 0 before the binary point. But if our exponent is the bit value 1, subtract 127, we still get 2 to the power of minus 126. But we multiply that by 1 point and then the mantissa bits. And this is how we get our representable range from 0 to some value. And actually, we can find out which value that is. Let me just complete this. There, not quite sure how to write this, but I hope you get this. All right. So on the higher end of our possible exponent values, we have all ones. And that's 255 minus 127. And that's 128. But it turns out that there's actually a second special case. And that is for infinity and nan. And I think it's a bit too early to get into exactly what specifically nan is. But for now, you should know that this is a value that can be the result of certain arithmetic operations that you perform on floats. For example, if a mathematical operation isn't allowed, like mathematically, like a division by 0, you would get nan. And there's like a whole world of things around that, because you can enable like fast math modes that have special handling of this. But for now, let's just say it's a special case, and that's good enough for now. So the second highest value is 254 minus our bias of 127. And that's the value 127. So if we just do an example for this one as well, just to have it complete, we would have 2 to the power of 127 times 1 point, and then our mantissa bits. We can see that the highest, like the greatest representable value, is almost, but not quite, 2 to the power of 128. So 2 to the power of 127 times 1.111, 23 ones, so almost 2 to the power of 128. And again, then we have our negative range with the sign bit set. So our entire representable range of numbers is from almost, but not quite, minus 2 to the power of 128 to positive, but not quite, 2 to the power of 128. And then, of course, we have infinity. And minus infinity, by the way, as well. There's also negative 0, but all right. The next thing I want to do, I want to talk about a real-life concept to try to make the bridge to floating point addition. And that real-world example is of kilometers, meters, and millimeters. Or, for example, gigabytes, megabytes, kilobytes. It's the same concept. For example, if you have 1 gigabyte, you could write that in a different way as 1 times 10 to the power of 9 bytes. Or 1 megabyte would be 1 times 10 to the power of 6 bytes. And for kilobyte, it's the same thing, but 10 to the power of 3. And our floating point value works kind of similar to that, where this leading 1, or it could be any value if you have, for example, 2 kilobytes, is this factor in front. And then we have this 10 to the power of some exponent that we multiply that by. And the result of that is our actual numeric value. Now, if you want to add two numbers together, you can't just do 1 gigabyte plus 1 megabyte and just add the two ones together. What you first have to do is you have to kind of get them into the same exponent or the same unit. Meaning, if you want to calculate the sum of 1 gigabyte and 1 megabyte, you would do the following. You would have 1 times 10 to the power of 9 bytes plus, and now you want to turn our value, 1 times 10 to the power of 6, into something times 10 to the power of 9. So how do we do that? Well, mathematically, it's allowed to, for example, do the following. We have the value 4, as an example, times 2 times 0.5. 2 times 0.5 is just 1, so we have 4 times 1, 4 is equal to 4. So we can apply the same concept here. We multiply our exponent factor, the 10 to the power of 6, by 10 to the power of 3, giving us 10 to the power of 9. So we have something times 10 to the power of 9, and that something is just 1 divided by 10 to the power of 3, which is, well, the same as 10 to the power of minus 3. Sorry. No, actually, it is 3. And that is just 0.001. And that's probably what you would have done in your head. 1 gigabyte plus 1 megabyte, you get the megabyte converted to gigabytes, and then you can add those two numbers together. So you would have 1.001 times 10 to the power of 9, so that many gigabytes. And you could also go the other way. You could convert gigabytes into megabytes and then have 1001 megabytes as your result. And you can do the same thing with the result here. Again, the gigabytes is just 10 to the power of 9. You can multiply that. You can multiply your 10 to the power of 9 by 10 to the power of minus 3, giving you 10 to the power of 6. Multiply your factor by 10 to the power of 3, giving you 1001, and you would have the number in megabytes. All right. I think this is actually enough to be able to implement addition for floating point numbers. So let's try to do that. Let's create a function. Just going to call it add. It's going to get two floating point numbers. And first thing, we're going to convert that to our union type. And we're going to do that for A and for B. And we're going to assign the float value, that's our input, to the floating point member of our union. Actually, let me just have a look if I'm still visible. That looks good. Same thing for B. And now what do we have to do? We need to analyze the exponents of our true values. And we need to shift the mantissa of one of the values so that the two exponents are the same. And now we have a choice that we also had before of shifting on one side and decrementing one exponent, or shifting to the other side and incrementing our exponent. Did I say decrement before? We do the opposite. So let's think about that for a second. Which one of the two is better? If we shift our mantissa to the left, that means that we will need a very large number of bits to be able to represent the resulting shifted mantissa value. So for example, the difference between two exponents could be quite great. Like we have a possible range of exponents from minus 126 to 127. So let's say we do that. And let's say we have enough bits to be able to do the addition. Our resulting value still has 32 bits, meaning we would need to cut off the least or the lesser significant bits of this resulting value to be able to create a result, like a resulting floating point value with 32 bits. So that doesn't seem like a very good solution. We are shifting to the left and like we need all these bits and then we cut off most of those bits again for the result. We go the other way and shift one of the two mantissas to the right. We just, like we have a maximum value of bits that we need to add. Like we can never add more than 24, and I'm going to explain why 24 bits in a second. We're never going to have more than that. So that, I think, is the better way to do it. Oh yeah, I want to explain why 24 bits. We saw earlier that we had one extra bit that is implicit in the representation, where we multiply our 2 to the power of exponent times 1 point and then the mantissa bits. And we do actually need to include that one leading bit when we add the two mantissas together. For example, you can imagine the floating point value 1 would be 2 to the power of 0 times 1. And the floating point value 2 would be 2 to the power of 1, and the mantissa bits set to 0. And in that case, we would have 23 zeros. So that's our actual, like, represented in bits mantissa, and we have a leading 1. And if we sum those together, we would get this. So we actually need to account for one more bit that can come into existence after the addition or with the addition. Yeah. And this implicit bit is at position 24. And this one is at position 25. All right. So we've chosen that we're going to shift to the right. But which value do we have to shift to the right? Now, shifting to the right is the same as dividing by 2. So if you have, for example, the value 4 represented as 0, 1, 0, 0, and then the value 2, you can get from 4 to 2 by shifting to the right by 1. So if we shift one of the values to the right, we have to kind of account for that by incrementing the exponent by 1. Each bit shift to the right means that we have to increase our exponent by 1 to still have the same number. So if let's actually create a separate value that's going to be a exponent, and that's going to be the integer representation shifted to the right by 23. So we're shifting out our mantissa and ending that with 255, so 8 bits set to 1. And we're going to do the same thing for b. All right, if the exponent of a is smaller than that of b, a is smaller than b, we shift. Let's actually also create the mantissa. U32 not shifted, actually. Just end it by 1 shifted by 23 minus 1. If you've not seen this before, this is a very useful trick to create bit masks. So, for example, 1 shift to the left by 4 minus 1 is 1. After the shift, we're going to have this. And then minus 1 gives us this mask. So that's just a thing that's good to know, how to create masks for bit operations. This is the mantissa of b. We're doing the same thing there. And we shouldn't forget about our leading 1. So there was one special case where the exponent is 0. But otherwise, we need to add the implicit 1. Actually, scroll down. So we need to OR our mantissa with 1 shifted to the left by 23. And the same thing for b. Sorry. All right. So now we can take our mantissa and shift it to the left by b exponent minus a exponent. And since a is smaller than b, we are guaranteed that this gives us a positive value. Okay. Otherwise, we're going to test if b exponent is smaller than a. And in that case, we're going to shift the mantissa of b to the right. Okay. We also need to count. Let's actually just create another value that's going to be our resulting exponent. And in here, we're just going to assign to that. And in this case, we're going to assign the exponent of b, because we're trying to bring a's exponent up to be at the same level as b. in this branch. And in this branch, we're doing the same for A. All right. So now we have the same exponents, which means we can now sum our mantissa, or the two mantissa values. Now, for now, I'm not going to look at negative values. So let's just do this. We create a value for our mantissa. And it's going to be mantissa of A plus the mantissa of B. All right. So if you remember from earlier, where we were summing the value 1 and 1, getting the resulting value 2, the value 2 was represented as 1 0 point and then a bunch of zeros. Which means if we now took the lowest 23 bits and copied those into our resulting mantissa bits, we would have all zeros. And we would have still the same exponent. Actually, we haven't even accounted for that case. If the two exponents are the same, we actually need to set our resulting exponent to either of them. Doesn't matter. So in this case, we would get the same exponent. So 1 plus 1 would be 1. That's obviously not right. So we need to check if the bit at position 25, so one shift to the left by 24, of our resulting mantissa is set to 1. And if it is, we have to shift our mantissa to the right by 1 and increment our resulting exponent by 1. All right. Let's just try if this works. Actually, we first need to create our resulting complete value, like the actual floating point value. So I'm just going to create another variable of our union type. I'm just going to call it nr for result. And we're going to assign the following thing to the integer member. We're going to take our resulting exponent, shift it to the left by 23, and OR that with our resulting mantissa. But we actually need to be careful that the last, or the 24th bit of our mantissa is not copied. So we need to AND this with 1 shift to the left, 23. Again, this is just our mask. Okay. Let's try to return the floating point member. And here I just want to print our two input values and the resulting output value. So let's just try to add 1 and 1. And let's see if this works. There are probably a bunch of syntax errors, but oh yeah, I didn't actually run it. Oh, okay, that actually worked. 1 plus 1 is equal to 2. Let's try more values. All right. 1 plus 1.5 is 2.5. Cool. Let's try to make this work for negative values as well. Now, what happens with negative values? I think what we need to do in that case we need to copy the sign bit from the float to our integer value. And then we should be able to just add the two values. Let's try this out. Let's make these signed integers. And let's look at our first floating point value in its integer representation. And let's take its sign bit. So one shift to the left by 31 is the last bit. And if it's set, I'm gonna multiply it by -1. I'm actually not sure if this will work. Let's do this here. And let's do the same thing for B. B, if the sign bit is set, we take the mantissa and multiply it by -1. The resulting mantissa is going to be a signed integer as well. And if the result is negative, we have to take the result and multiply it by -1 as well to be able to, like, we don't want to copy the 2's complement representation into our floating point value, but we want to keep the information that our result is negative. So I think here I'm going to create a value that's like is negative. So if the resulting mantissa is negative, I'm going to set this value to true. And again, multiply this by -1 to get a positive value out of this. And if our value was negative, we're going to OR our floating point value with our sign bit. Otherwise by 0. And actually we have to be careful here. This has to be unsigned. Let's just try this. I'm not sure at all if this works. 1 plus -1.5 unkit identifier bool. Yep. Let's include standard bool. Okay, 1 plus minus 1.5 is not minus 1.5. So this doesn't work. Let's have a closer look again. We're getting our mantissa correctly. We're getting the exponent. Okay. I think that part should be fine. And if the sign bit is set, we multiply our value by minus 1. Actually, I just saw an issue right here. I made the same mistake that I tried to not make down here, where I was shifting the integer value 1 to the left by 31. All right, I've had a look through this, and I think I know where our issue is. What I've done right here, I've taken our two input values, 1 and minus 1.5, and I've kind of followed through this calculation. And I'm just printing the resulting mantissa in hex after the multiplication by minus 1 to make it positive. And this is what we see. We see 4 followed by 5 zeros. Each 0 is 4 bits. So we get 20 zeros and then 2 zeros. Like the 4 is 0, 1, 0, 0. So 22 zeros and then 1. And that's sort of interesting, because if, again, we just kind of try to write down what these input values are in hex, we get 1, which is just the exponent value 0 and the mantissa of all zeros. And so let me just write this down. Exponent 0, which means the bit representation is 127 minus the bias of 127, so 0. And our mantissa is 1 point and then 23 zeros. And minus 1.5 is again an exponent of 0, because 2 to the power of 0 is 1. And now our mantissa is 1.1 and then 22 zeros, which is 2 to the power of 0, so 1 times 1.5. 1 times 1.5. And this is just 1 times 1. So, and the sign bit obviously for the last one is set to 1. But our resulting value has the following mantissa. It has now 0.1 and then a bunch of zeros. So basically the resulting exponent seems to be less than the exponent of the two inputs. Because one rule, as we learned earlier, is that the mantissa always has this implicit 1 point, except for this one special exponent value. But here, our mantissa has a leading 0. So to account for that, we need to shift this resulting mantissa to the left until we have some value where there is like a 1 point and then the mantissa bits. And then we can copy the lower 23 bits into our resulting floating point value. Let's just keep this here. And to try out our thought and see if this actually works, let's just write a for loop. Maybe that's probably the easiest thing. It would start. Maybe let's write a while loop for this, actually. Yeah, I think what I'm currently thinking about, there can never be a bit set to 1 beyond the bit at position 25 after the addition, which means we actually have an else case here. And in this else case, we will have some kind of for loop. For now, I'm just going to do while true. Actually, we can just do the resulting mantissa. Like what we want to have. We want to have a bit value 1 at bit position 24. So 1 shift to the left by 23, and it with our result mantissa. If that is no, if it is 0, then we need to shift our mantissa to the left until it's not 0, in which case we would exit the loop. So with each loop iteration, we would shift our mantissa bits to the left, and shifting to the left is multiplying by 2. So we need to account for that by decrementing our exponent. So after 1 iteration, for example, for this value, we would be at 1 point and then 23 zeros. And our exponent would be decremented by 1 to account for that. So let's try to do that. We're going to shift our mantissa to the left by 1. And decrement our exponent. Now, one thing we have to be careful with is if our exponent, the resulting exponent, is like at the negative end of our range. We don't want to decrement our exponent past minus 126. And I'm actually kind of contemplating if it's a good idea to focus on this at first. For now, we're going to keep this in mind, but I'm not going to handle that special case for now. I think we need some extra condition here. That's like, if the resulting exponent is minus 126, also exit from the loop. And then later we can check if that was true. And oh no, actually we should handle that. Because our exponent is an unsigned integer, and we really shouldn't decrement it if it's currently 0. So if it is greater or equal to 1, we would decrement it to 0, and that's okay. I think actually this might be enough to handle our special exponent case. But I'm not quite sure. We should check this later. Okay. Maybe let's just run this to see what we get. Lower precedence than absolutely. Let's put parentheses around, maybe around everything. And it with 1 shifted by 23. That's equal to 0. Yes. All right. That looks good. 1 minus 1.5 is minus 0.5. Let's try more values. Let's try 2 and 2.5. 4.5. Awesome. Let's try 2 negative values. Awesome. Minus 2 minus 2.5 is minus 4.5. I think I'm happy with that. I'm thinking if we should try values with an exponent of 0 as well. Let's just, I don't think it'll take too much time to do that. And I'm kind of curious. Let's create a value A and let's create a value B. And to the unsigned integer member of A, we're just going to assign the value 1. And to B, we're also going to assign 1. And what I've done here is I'm setting the exponent to 0, and I'm setting the least significant bit of the mantissa to 1. And the sign bit is also at 0. So what we should get now is the bit value 2. Like, if we reinterpret our output float as an integer, we should get the value 2. And that will kind of make sure that our while loop here is correct, which I'm not sure of at this point. So let's assign the result to f, and let's call add with our 2 floating point values. And I'm just going to print the result as a hex value. Actually, we need to do this again. And we're going to assign to the floating point member Actually, I can just do this. All right, and let's try to read the integer part. And we get 2. Cool. So I guess this seems to work. I'm sure there are still edge cases. We haven't thought at all about infinity and nan and other special cases. But I think I'm happy with this for now. So as a next step, I think we now have actually enough knowledge to be able to implement the inverse square root algorithm. But before that, I'm going to take a quick break. All right, let's try to take this knowledge that we've gained so far and implement the inverse square root algorithm in the style of Quake 3. And for that, I'm going to create a new file. I'm going to call it r_root.c. Just going to include standard IO again. And actually, let me just copy our union from here. Let's try if this works. Definitely need to include standard integer again. And sorry, hopefully that should be fine. r_root.c. Output is going to be r², and we're going to call that. All right, looks good. Okay, so what is the inverse square root? You can write this as 1 divided by square root of some value. And this is, for example, used when you want to normalize a vector, meaning you have a vector of a certain magnitude, of a certain length, and you want to normalize that to have a length of 1. That means that you have to take each component and divide it by the length of the vector. Now you get the length of the vector by taking the square root of each of its components to the power of 2. So you would basically take one of your components and multiply it by the inverse square root, like this. This is one possible use case. And turns out that you have one division and one square root in here. And doing these operations on floating point numbers is pretty expensive. So when it was creating Quake 3, they come up with a way of doing the same operation with CPU operations that are less expensive. And what they did is they took advantage of some very interesting behavior or very interesting characteristics of our floating point representation. And for that, I think we should look at our graph from earlier again. Let's go into main.py and let's create this again. And we saw last time that this looks very much like a logarithmic function. Not quite, because it has these flat line segments in between, and it also doesn't cross 0 at the x value 1. But otherwise, the general shape looks quite similar to a logarithm. And this is actually really interesting to think about. We have taken floating point values, in this case uniformly spaced from 1 to 1 million, and we have reinterpreted their bits as an unsigned integer. We've not performed any mathematical operation. We've just taken the same bits and just read them as a different type. There's no CPU instruction involved in this. We're just taking the same bits and giving them a different meaning. But just by doing that, just by giving those same bits a different meaning, we've actually performed something very similar, an approximation of a mathematical operation, of the logarithm. And it's a really interesting and very, very powerful technique. So in the context of our inverse square root, how does this actually help us? Well, it turns out that there are a couple of mathematical rules that relate operations on certain values to operations on the logarithm of those values. So those rules, for example, are that if A times B is equal to C, how am I going to write this? That implies that the logarithm of A plus the logarithm of B equals the logarithm of C. This is a rule that applies. For example, if we have, just to try this out, if we have 4 times 8 equals 32, if we take the log 2, so 2 to the power of what equals 4, 8, or 32, 2 to the power of 2 is equal to 4. So we have 2 plus 3, because 2 to the power of 3 equals 8, equals 5. And that's correct. 2 to the power of 5 is equal to 32. And there are more rules like this. So for example, A divided by B implies that log of A minus log of B equals log of C. Let's try this out as well. So 8 divided by 4 equals 2. And the log 2 is 3 minus 2 equals 1. There's another rule that is A to the power of B implies that B times the logarithm of A equals logarithm of C. And let's try this out. If we have 2 to the power of 3 is equal to 8, we have 3 times log of a, in this case it's just 1, equals log 2 of 8, which is 3. 3 times 1 equals 3. Let's do this for 4 to the power of 6. Well, actually, what is 4 to the power of 6? 4 to the power of 3 is 64. 64 is 2 to the power of 6. So it should be 2 to the power of 12, which is 4096. Is this correct? I'm just going to check my calculator. 4 to the power of 6. Yep, that's correct. Okay, so we have 6 times log 2 of 4 is 2, and that's 12. 2 to the power of 12. All right. And the last rule that is of interest to us is, how do I draw a square root? All right. Let's do maybe this and this. This is all right. We have to live with this. A square root is just, for example, the square root of 4 is the same as 4 to the power of 1/2, so 1 divided by 2. And the cube root is the same as some value to the power of 1 divided by 3. That's all we're doing when we are taking a square root or a cube root. It's just taking that value to the power of 1 divided by 2 in the case of a square root, 3 in the case of a cube root. As we to see, that implies that we have 1 divided by b times log a is equal to log c. And you can see that this is kind of the same rule as before. Like the same rule as this. And this is also kind of the same as this. And actually all of these are kind of the same. But it's still good to know, or good to have these as separate rules. And this is interesting. Because let's think about how we could represent our inverse square root as logarithms. An inverse square root, or first of all, an inverse. So if we want to create the inverse of a, we take a to the power of -1. And that is 1 divided by a. So the inverse. So if we want to create the inverse of a square root, well, actually let's do the square root first, which is a to the power of 1 divided by 2. That's square root of a. We create the inverse square root by basically doing a to the power of 1/2 and that to the power of -1. Now, if you have something to the power of, like a to the power of b to the power of c, that's the same as a to the power of b plus c. Sorry, b times c, meaning our inverse square root is really just a to the power of minus 1/2. That's our inverse square root. I hope this was kind of understandable. I think this would be better if I had like a drawing pad, but hopefully you kind of get the idea. And this is interesting because we can now take this representation, a to the power of minus 1/2, and write it in terms of a logarithm. And we're going to use this rule right here. So a to the power of minus 1/2 represented in terms of a logarithm means that minus 1/2 times the logarithm of a equals the logarithm of the result of the inverse square root. And this is very appealing because we saw earlier in the diagram that we have access to something that looks very much like a logarithm just by taking the same bits and interpreting them as an unsigned integer value. And adding a certain bias because you saw that the value at x1 wasn't 0 as we wanted. Actually, let's have a look at that. Let's think about the floating point value 0.0. How would that be represented in bits? Since our exponent is biased by minus 127, that means that our actual bit value of the exponent should be sorry, this is actually not what we want. We want the bit representation of the value 1 because for the floating point value 1, we want a logarithm value, like an approximation of the logarithm of 0. So what is our bit representation for the floating point value 1? It means that our exponent is 0. So bit representation 127. And 127 means that our sign bit is set to 0. Or the fact that our number is positive means that the sign bit is 0. And then 127 is just a 0 and then 7 ones. And then we have all zeros in the mantissa. So that means that to get our approximation of the logarithm function, we can do kind of the following thing. Let's say we have our x value, which is a float. We would take the bit representation of this value, interpret it as an integer, which would give us a very large integer value. It would give us this value interpreted as like a 32-bit integer, which is somewhere around 1 million, 1 point something million. Actually, I think it's 1,000. Yeah, I think it's in the, yes, it must be, it's definitely in the billions. because maximum integer value 32-bit is 4.2 something billion. So at this point we have 2 billion, 1 billion, 1 point something billion. So we need to subtract that very large value from our bitcast float to get somewhat of an approximation of the logarithm of x. Okay. And that also implies that to reverse this operation means, so if we have our if we have some other value y, and we do y plus some very large value, and then take the, sorry, this is actually an unset integer, and then we take those bits, actually let me make this a bit clearer, bits as u32, and here I'm going to do bits as f32. That is very close, like that's an approximation of the exponent function. So kind of the inverse. So we basically now have all the building blocks to start thinking about what our inverse square root function would look like if we expressed it in terms of these logarithms and bit operations. Actually, I want to think about this again before we do that, just to make sure that this is actually correct. We have some integer value y, which, for example, would be about 1 billion. And to get the exponent value, let's say y is equal to 0. 0 plus 1 billion, interpreted as a float, would be 1, which is correct. E to the power of 0, or anything to the power of 0, is 1. So yeah, this should be good. Okay. So let's take this equation right here, the mathematical representation. Let's try to incorporate our bit operations into that. So first, I'm basically we're just going to apply this pattern here to this function. What we need to do to get c, just going to rewrite this, is to apply the exponent function to both sides of the equation. So like this gives us the result of logarithm of our actual wanted answer. So to get the actual answer, to get c, we need to do exponent or exponential function of minus 1/2 times log of a. Okay, and now we we basically just take these functions that we have down here and start substituting. So to get C, we apply the exponent function, which is our bits, our integer bits, interpreted as a float of some value y plus our very large value k, which is just this. Actually, let me just write this. K is equal to this very large integer value, which again is just the integer representation of the floating point value 1, which is the point where our exponent, like the logarithm function, is 0. Something to the power of 0 is equal to 1. Okay, so this is our k, and our y is now minus 1/2 times, and then the logarithm of our input. Let's just call this output and input just to make it clear. So we have the bits as a U32 of our input minus k. Just substituted. Maybe let's do this in more steps. I think that might be a bit clearer. Let's this logarithm of our input. I hope this makes it a bit clearer. So we've just substituted the logarithm of our input with bits as U32 minus k, which is just what we've written here. And this is kind of all we need to do. We have 2 bit casts in here, which again are free. We have one multiplication, subtract, add. So it looks very, very simple. And in fact, we can actually simplify this even further by, like, I kind of want to try to get these 2 k's to hopefully become one number. Let's just try to do this step by step. So we can just do bits as U32 divided by 2 minus plus k divided by 2. And after that, we can remove this. 4, 1, 2, 3, 4. Yeah, I think the parentheses should be balanced. And now our division by 2, as we discussed before, that's really just a right shift by 1. So we take our bits, shift them to the right by 1, thus dividing them by 2. Take the negative of that, multiplied by minus 1, and add to that k divided by 2. We could also shift that to the right by 1, plus k. And we can now actually remove these parentheses. And now we can merge our k divided by 2 plus k, which is just 1.5 times k. And now we've quite drastically simplified our equation. Now 1.5 times k is actually going to be a bit difficult because we are dealing with integers here. K is an unsigned integer, and our bits as U32 also results in an unsigned integer. So how do we multiply by 1.5? Now multiplying by 1.5 is the same as multiplying by 3 and then shifting to the right by 1, thus dividing by 2. So the way we can write this as well is by doing 3 times k, shifted to the right by 1. And I think that's about as far as we need to simplify this. And actually we could take our k and kind of pre-calculate that, like just have a constant for that. But for now, let's just focus on writing the function at all. So I'm just going to create a new function here that's going to return a float. I'm going to call it r square root. And it's going to take one float as its input. And now the first thing we're going to do, we're going to perform this bits as U32. So I'm just going to create a union or a variable of this union type again. And I'm going to assign our input value to its floating point member. And now we can start performing these operations. So first, we want to shift our unsigned integer representation 1 to the right. I'm just like taking this line right here and translating it into C code effectively. We want to multiply that by -1. To get the negative, or not negative, just multiply it by -1, basically. Like if it's negative, it becomes positive. If it's positive, it becomes negative. And we are going to add to that 3 times. And now let's try to write this as a hex value. So to write this as a hex value, we're just going to try to write it as like buckets of 4 bits. So we have 0011, then 4 more ones, then 1 more. 3, 4, 1, 2, 3. Yep. Okay, so that's 3 F8, and this is not news to us, actually. We saw this a couple of hours ago. And the rest is going to be zeros. So here we have 16 bits and then another 16 bits. 3 times that shifted to the right by 1. And now we can just return the floating point part. or rather the floating point interpretation of these bits. Let's just try and see what that gives us. So I'm just going to create some input value here. This is going to be hopefully uninteresting, this value. Going to call our reciprocal square root function on that. And let's try to compile and run this. Incomplete type, union F32, U32. Actually forgot to... Oh, okay. It's just further down. All right, let's try again. Overflow an expression. This is an interesting thing. This hex value, by default, is going to be of type signed integer, signed int. And in fact, I can show you a bit of a trick to kind of verify that for yourself. This is actually kind of good to know in general. If you want to know a numeric value at compile time, you can do the following thing. C has a syntax for returning arrays from functions. And it looks like this. It's a valid syntax, but it's actually not valid C. So what you get when you try to compile this is you get an error that the function cannot return array type int 0. But it turns out that you can actually put, for example, size of in here. So size of int, we're expecting 4. And we can actually see this value 4 in our error message. That's a very useful thing. So if you ever want to get like a size of a type at compile time, this is a trick that you can apply. And the same thing actually works for types as well. So I'm just going to put 0 as the array count. And it's going to be an array of type of, let's just say 0. And we can see that our error message says aka int array. So we can just take our constant here, copy it, paste it in here, and we see that our constant is of type int. Now that's an issue because multiplying this constant by 3 is going to result in a value that occupies the last bit in those 32 bits of an integer. And that bit is the sign bit. And that's not what we want. Actually, we can even go into a bit more detail on that. We saw that our constant value, our k, starts with 0, 0, 1, 1, as we had here. Multiplying that value by 2 is going to give us at maximum, the maximum value that we can get occupies the second highest bit. And in here, there could be anything. Multiplying by 4 is going to give us a number that occupies the very last bit, and then some other values in here. Meaning that shifting our number by a certain number of bits kind of gives us an upper bound for how many bits we're going to occupy in the resulting value. That's why it should be, or could have been clear to us that multiplying, or it could have been a hint to us at least, that multiplying by 3 is definitely going to occupy the second highest bit, but also very likely will occupy the very last bit, thus going into our sign bit. This is just like a trick for kind of guessing how many, or approximating how many bits your multiplication result is going to take. Anyway, this is very easy to solve. We just have to append a u character here to make clear to see that this is an unsigned integer constant. Let's try to do this. And this doesn't look terribly broken. Our input is 1, and our output is 1 as well. And if we do the actual mathematical operation, we would have 1 divided by the square root of 1, which is 1. Let's try this for some known value. Let's do 1 divided by the square root of 4 should be 0.5. And that looks pretty good. All right. Let's try to compare this to the actual implementation. So let's do real out. And what I mean by real out is just doing the calculation ourselves with square root f, and I think I need to import method h. Yep. Include method h, and we get the same result. 0.5 for both. Okay, let's try 9. We should get a value that's very close to 0.333. And our real inverse square root does do that, but our inverse square root gives us a slightly higher value. Let's try more values. Let's try 2. And again, we're not terribly far off, but we are not as accurate as the actual calculation result. Let's try 0.5. Okay, we're still like somewhat close, not terribly far off, but also not the same. So this comes back to what we were exploring earlier, where interpreting the bits of a float as an unsigned integer looks something like a logarithm, but it's not quite a logarithm. It has these like flat line segments in between. So it isn't like an actual logarithm. It's an approximation. But we can actually make our guess a bit better, because there are methods of basically taking a function result, or like a guess for a function result, and getting closer to the actual result. And one way to do that is called Newton's method. And the way Newton's method works is it is meant to find roots of a function. Meaning, like, finding a root means that you want to find an x value of a function where that function returns 0. It's like you're crossing with the horizontal x-axis. Okay, if we have some function f of x, we are looking for an x where f of x is equal to 0. But our function, our inverse square root, isn't supposed to be 0. So we need to find some way to kind of invent some function that is going to be 0 when we've done our job correctly. And what we could do is we could take the inverse of our function, apply that to the result that we think is correct. And if we are actually correct, we should get back the original input value. Let me try to write this down. So our inverse square root looks like this. And if we now take this whole thing to the power of 2, we get 1 to the power of 2 divided by x. And if we take 1 to the power of 2 divided by x, and which is, by the way, just 1 divided by x, and take this to the power of minus 1, we will get x. Which means we can invent a function that is basically the invert or the inversion of our function. And then we can take the result of that, which should be equal to x, minus our original input value, and the result of that should be 0. So we will have a function that is defined in terms of r, our result, like the result of our inverse square root. And taking that result to the power of minus 2, because, again, 1 divided by the square root of x to the power of minus 2 is equal to x. Because we've first taken it to the power of 2 and then to the power of minus 1, meaning we can do 2 times minus 1, so minus 2. So r to the power of minus 2, we expect this right here to be equal to x. So x minus x should be 0. So we've now created a function that we expect to be 0 if we've done our job correctly. Now let's have a look at the definition of the Newton-Raphson method. And we can see that it's defined as our next guess for an x value. In this case, the next r value, like our result of the inverse square root, is the current value of r minus the evaluation of our function divided by its derivative. Let's write this down. Our next r value, again, r is the result of our inverse square root, is our current r value minus f of r, which is this function right here, divided by the derivative of that function. So let's try to write down the derivative. F derivative of r is minus 2 times r to the power of minus 3 and that's it, because x in this case is a constant factor. It's not part of our it's not a function variable. So this is our derivative. So let's just write all of this down. R next is equal to R current minus f of r, which is r to the power of minus 2 minus x divided by minus 2 times r to the power of minus 3. And that gives us a close approximation of our inverse square root result. And let's just try to implement it like this. So the F32 member of our union N is, in this case, R. So the next R is the current value minus F32 to the power of minus 2. So that's already a bit unfortunate, because that's kind of hard to calculate. So let's try to minimize this function just a little bit. Minus 2 times r to the power of minus 3 is minus 2 divided by r to the power of 3. So that whole thing as basically we can take the inverse of this part. Let me just try to write it down first and then I can explain. We would have minus 2 here, and our r to the power of 3 would be here. Of 3. Okay. So now we have r to the power of minus 2 minus x times r to the power of 3. And we can minimize this further, because r to the power of minus 2 times r to the power of 3 is just r. So we have r minus x times r to the power of 3 divided by minus 2. Again, I'm kind of sorry that I don't have like a tablet to write on. I think that would be a lot easier, but I hope it's still kind of understandable. Yeah. Times r to the power of minus 3 is like dividing by r to the power of 3. And we're taking this division and kind of inverting it. This is just a rule that you can apply to minimize the function. And now we can go even further. And actually, maybe let's just try it like this. This is already a bunch simpler than it was before. Or at least simpler to implement. Actually, maybe there's one. We have a division by -2. So basically, we can just rewrite this as plus divided by 2. Okay, let's just try this. And actually, we need another pair of parentheses here. Division by 2. X is our original input value times, there's still left room for optimization here. But let's try what we get with this. The semicolon here. Yep. Okay. And it seems like we are a bit closer. So if we just comment out this line again, we were at 1.5. And now we are at 1.406. It's a lot closer to the actual result. And let's just try to make another iteration of this. Okay, now we're actually pretty close to the real result. Now, let's try again for a second to optimize this a bit further, because we still have a division by 2. We could swap this out for a multiplication by 0.5, but I think there's room for more optimization. The first thing we can do, we can factor out our R value here and make this R times 1 minus R to the power of 2. And that gives us -0.5 minus 0.5 times x times R squared. And I have a feeling that there's a better way to optimize this. Let's just go with this for now. Okay, so we have our F32 part again. times 0.5 minus 0.5 times our original value times r squared. And let's see if this even works. This should be n. And it does seem to still work. Now, one thing we might be able to do here is, like, because r current and the r, I've written them as differently named things, but they are the same. Like, r current is just r. In fact, to make it clearer, this is just the same. So I think we can rewrite this as r times 1 plus 0.5 minus the rest. Yeah, okay, this should work. So then we have r times 1.5. And let's try this. Times 1.5. Sorry, this was still needed. 1.5 minus 0.5 times. Okay, let's see if this works. Does seem to work. Let's do more iterations. And we get very close to the actual result. And we have minimized our function quite far. Actually, we can go a little bit further. We can create like a temporary value that is r squared. And we can... Sorry, that's actually not possible because r is updated with each iteration. But we can factor out 0.5 times a at least. So that's a divided by 2. Not that it really matters, but it is a bit of an improvement. Still the same value. Let's see how far we get with 2 iterations. Very, very close. So this is pretty cool. We have basically a way to trade performance for accuracy. If we need just like a very rough estimate, we can have no optimization at all. Just leave out these 2 lines. If we want a bit closer to the actual value, we can have 1 line. Otherwise, 2 or more, depending on what we want. So I'm actually quite happy with what we've achieved today. We've kind of gone over the theoretical basics of floating point values. We have looked at the relation between a floating point value and its integer bit representation. We have implemented the floating point add operation ourselves. And we have kind of rederived the inverse square root algorithm that is used in Quake 3. So I hope that you've learned something, or that you had fun while we were doing this. Yeah. Thank you very much for watching, and see you next time.